Have you ever wondered if scientists can predict earthquakes? It's a thought-provoking question, isn't it? Imagine a world where the destructive power of earthquakes no longer catches us off guard. Intriguing, yet it brings a flurry of questions. How does the science behind earthquake prediction work? Is it even feasible, or are we chasing a myth? The answers lie in the fascinating field of seismology. So let's not wait any longer. Let's dive into the world of seismology to find out. Seismology, the study of earthquakes, is a complex science. It's a field that delves deep into the mysteries of the Earth, exploring the forces that shape our planet. At the heart of seismology is the understanding of tectonic plates, these massive slabs of solid rock floating on the semi-fluid layer of the Earth's mantle are constantly in motion. They slide past one another, collide or pull apart, and it's these movements that trigger earthquakes. Picture two enormous puzzle pieces grinding together. The friction holds them in place until pressure builds up, and they suddenly slip, releasing a tremendous amount of energy. This energy travels through the Earth in waves, causing the ground to shake. And that's an earthquake. Scientists use a variety of tools and techniques to study these seismic phenomena. One key instrument is the seismograph. This device measures the intensity, duration, and direction of these shaking movements. When an earthquake occurs, the seismic waves cause the seismograph's pendulum to move. This movement is recorded as a series of peaks and valleys on a graph, creating a unique fingerprint of the earthquake. In addition to seismographs, scientists also conduct fault studies. They examine areas where tectonic plates meet, known as fault lines. By studying the history of earthquakes along these lines, they can gain insights into patterns of seismic activity. These tools and techniques provide valuable data, enabling us to understand more about how and why earthquakes occur. They help us to map the Earth's tectonic plates, identify high-risk areas, and even provide some warning when seismic activity begins to increase. However, while we've made significant strides in understanding the how of earthquakes, the when remains elusive. Despite our advanced tools and deep knowledge of tectonic movements, earthquake prediction is still a field fraught with uncertainty. But the million-dollar question remains: can we predict when the next big quake will strike? Predicting earthquakes is not as straightforward as predicting the weather. You see, the process of earthquake prediction involves a complex array of factors that, at present, seem to elude our understanding and technological capabilities. First off, earthquakes are inherently random. They can occur anywhere, at any time. Unlike a storm brewing over the ocean, we can't see an earthquake coming. It's like trying to predict the roll of a dice, but the dice is buried deep within the Earth's crust, invisible and unpredictable. Speaking of the Earth's crust, its vastness presents another significant challenge. The Earth's crust is a complex, ever-changing structure riddled with faults and fractures. To accurately predict an earthquake, we would need to monitor every square inch of it, a feat that's currently beyond our reach. Then there's the precision required in prediction. Even if we could monitor the entire crust, we would still need to predict the exact time, location, and magnitude of an earthquake. That's like trying to find a needle in a haystack, but the haystack is the size of Earth and the needle is constantly moving. Finally, we face limitations in our scientific understanding and technology. Despite advancements, our understanding of earthquakes is still evolving, and our technology is not yet capable of detecting the subtle precursors of an earthquake. So where does this leave us on the question of earthquake prediction? Despite the challenges, advancements are being made in earthquake early warning systems. These systems are not about predicting when an earthquake will occur, but they provide crucial seconds to minutes of warning after an earthquake begins and before the strong shaking arrives. It's a race against time. These precious moments can allow people to take cover, halt trains, stop surgeries, and more, potentially saving lives and preventing injuries. The science behind these systems involves detecting the less destructive, faster-moving P waves that are first to emanate from an earthquake. This detection then triggers the warning before the arrival of the slower but more damaging S waves. Researchers around the globe are continuously refining these systems, working on algorithms that can more accurately read seismic activity and give people more time to prepare. The aim is to make these early warning systems faster, more reliable, and more widespread. So while we may not be able to predict earthquakes with complete accuracy yet, the future holds promise. In summary, earthquake prediction remains a complex and challenging field. We've journeyed through the intricate science of seismology, where hidden beneath the Earth's surface, seismic waves reveal the story of our planet's movements. We've grappled with the challenges in earthquake prediction, a puzzle not yet fully solved. And yet, there's the promise of early warning systems, a beacon of hope in the midst of uncertainty. As we continue to unravel the mysteries of our planet, who knows what breakthroughs the future may bring?